Greetings, podcast listeners. Jordan River here, back with you with more Growcast, the macronutrients to your brain garden. Today we have Nick back on the line. We're continuing our nutrient exploration, and we are wrapping up the soil fertilizer nutrients. Micronutrients are what we're covering today. Now, there are many micronutrients out there, a vast amount of them, but we focus on a handful, and we tell you why they're important in your cannabis garden. I know you're going to love today's deep dive, but before we get into it with Nick, shout out to Pulse Grow, baby. PulseGrow.com is where you can find the world's most advanced garden monitor systems. Code GROWCAST is still active. You can get savings on the best garden monitor system in the world. Now they have the new Pulse Hub, which allows you to not only keep track of all the other environmental factors that Pulse has allowed you to control, like temperature and humidity and dew point and vapor pressure deficit and light intensity, but now with the Pulse Hub, you can plug right into your medium. You can detect medium moisture, you can detect EC and things like this. It all goes into one nice, clean app. It's the best garden monitor system in the world. You can find it at pulsegrow.com, and I want to thank Pulse for hosting our Pestapalooza class at their amazing headquarters. It's a small team here in America, down in SoCal, and they invited us into their warehouse to teach a Pestapalooza class. It was an awesome Los Angeles class, and we want to thank Pulse for being not only the makers of an incredible grow monitor system, but also supporters of our community. So thank you to Pulse, pulsegrow.com. When you're ready to pull the trigger on the best around, you got to keep an eye on your environment, just like you got to keep an eye out for those pests. Pulsegrow.com, everybody, code GROWCAST. Thank you to Pulse. All right, let's get into it with Nick from Rooted Leaf. Thank you for listening and enjoy the show. Hello, podcast listeners. You are now listening to Growcast. I'm your host, Jordan River, and I want to thank you for tuning in yet again today. Before we get started, as always, I urge you, please help Growcast by sharing this show. Send this link to a fellow grower or turn a smoker on to growing. It's the most impact that you can make on the cannabis community, and it helps us out. See everything we're doing at growcastpodcast.com. There you'll find all the classes, the seeds, and the awesome membership. I do seriously appreciate all of you members and all of you listeners. Today we are continuing a series of nutrient deep dives. I know you guys love this series. We're getting into the weeds deep, and we're kind of rounding out a big portion of this series by moving into micronutrients. So, you know him, you love him, he's back on the line. Nick from Rooted Leaf is here. What's up, Nick?
Hey, Jordan. How's it going?
Excellent, man. Listen, we've got more of these nutrient deep dives to go through, but we're kind of rounding out the soil fertilizer element portion here by getting into micronutrients. You've done an amazing job so far through all of the different macronutrients and secondary nutrients. It's been awesome. And so I just want to thank you here for doing an awesome series. I'm really excited to get into these smaller, minute minerals with you.
Yeah, me too. And I appreciate all the support we've gotten over the past, God, I don't know how many episodes we've done so far. It's been, we've gone through all of the elements pretty much, and we've heard really, really positive feedback. So I just want to thank the audience as well. I'm glad you guys are getting useful information that you can apply to your gardens and start to see some benefits associated with just looking at things a little bit differently, understanding to a greater level what exactly is going on, and just knowing how to read your plants as a result of this. This is an awesome feedback loop for us, because it's one thing to just do these deep dives over and over again, but it's another thing to have so many people come back and say, hey, my plants are super healthy now. I kind of solved the problem, that I've been facing for a while now. So all that is super helpful, and I appreciate everybody's support so far.
It's been awesome, man. And just really quickly, if you enjoy these deep dives, and if you're not 100% satisfied with your nutrient regimen currently, go to rootedleaf.com, grab a starter pack. You'll never go back. You don't need a pH. They're loaded with carbon. Code GROWCAST for 20% off. Supports Nick, supports the show, and you will not regret it. Obviously, Nick knows what he's talking about, and I've been loving it, running those Rooted Leaf nutrients, man. So just real quick in the beginning here, rootedleaf.com, always code GROWCAST. But regardless of how you grow, we are here to educate you and continue these deep dives. I love a good deep dive. So let's get right into it, Nick. Micronutrients. Tell me why there is a classification that is specific as to what a micronutrient is, and what defines a micronutrient.
Micronutrients are really interesting. So in the grand scheme of things, the essential nutrients that are required by plants, all of them are required. It's not like one is more important than the other. But when you start looking a little bit more closely at what are some of the functions that are fulfilled, the macronutrients are taken up in large concentrations and they're used for a variety of different things. So you have a lot of enzymes within plants that might somehow interact with these elements and utilize them in a way that really benefits the primary growth and the secondary metabolic pathways, which we'll kind of get into a little bit. Micronutrients, even though they're just as essential as some of the macronutrients that we're more familiar with, they're required in much smaller quantities. And oftentimes the roles that they fill or that they serve in plants is going to be a little bit more limited than some of the other elements. So again, this is not to say that they're unimportant, but rather that their importance is more defined by, smaller concentration of them being present inside of the plants. And we'll kind of look specifically at what are some of the benefits of these micronutrients and what are some of the things that they're commonly associated with.
No, it sounds
I
amazing.
hope that provides a good definition for people.
Yeah, just literally they are utilized in smaller quantities by the plant. Therefore, they are a micronutrient. That makes sense. How small are we talking here? Like when you take a look at zinc and like how much zinc you need in your soil versus, I don't know, potassium, what does that ratio look like?
That's a good question. So it kind of depends. With the micronutrients, typically you find them in the range of like 1 to 10 parts per million, sometimes a little bit more. When you compare that against something like nitrogen or potassium, those two can be accumulated in plants in the several hundred parts per million. So it's not uncommon for us to see somewhere between 150 to 200 parts per million of nitrogen.
Right.
And we can be in excess of 300 parts per million of potassium. But when we're talking about iron, copper, zinc, manganese, molybdenum, even boron, these typically are more confined to, let's say, the 1 to 20 ppm range.
Wow.
Like magnesium is a good example. Magnesium and phosphorus, we would still consider those major plant nutrients. In fact, phosphorus is considered a macronutrient, even though it's taken up in pretty small quantities. But the optimum sweet spot, I guess you could say, for phosphorus nutrition in plants is somewhere around 30 to 50 ppms of elemental phosphorus. And magnesium is going to be pretty close to that as well. So, for the range of the micronutrients to be anywhere from 1 to 10, maybe 15 to 20, it's not that far behind some of the other elements. But still, I think a lot of people understand micronutrients are required in just very small concentrations relative to some of the other elements.
That's exactly what I was looking for, man. That's great. Where do these nutrients kind of occur and operate in nature?
They're found in all kinds of different soils around the world. They're typically present in the forms of rocks. And I think we kind of talked about this with some of the other elements. I think it was silica, where we kind of did a deep dive into various flavors of rocks that contain silica and maybe contain other types of minerals as well. Usually they're bound up, they're in more unavailable forms. And so they require some level of chemical weathering to be able to actually access and break down.
Like copper ore or something?
Yeah, just some kind of geological rock that contains maybe a complex array of different elements. It may contain silica, it may contain a little bit of aluminum, even to some extent, it may contain some of these micronutrients. And a lot of the ways that they're actually freed up is through the interactions that plants have by secreting some organic acids into the soil and contributing to the breakdown and the release of those elements. Again, they're not super concentrated, even in their parent forms, but humans, through their endeavors and activities in the fertilizer industries, have found clever ways to take some of these rocks and to digest them using acids like sulfuric acid, for example, and then precipitate these minerals out. So now we're dealing with compounds that may be more purified, like zinc sulfate or manganese sulfate, even iron sulfate and copper sulfate. These are all fairly common forms of micronutrients that you can buy in a bag, and they're typically a little bit more soluble than they are in their parent forms. But the idea basically is that whether it's been processed chemically by humans or it's found out in nature, the source is effectively the same. And I don't think you can get it without actually first dealing with some rock out there in nature.
Right.
That's what ultimately everyone starts with.
So let's get into these specific minerals, and I want to hear why they're important to cannabis. We're going to get into some micronutrients here, go over one by one. And what do they do for the cannabis plant? Why are they important to us as growers? And how can we kind of maximize the potential of these minerals? I got to start with silica. Man, silica is so commonly talked about in cannabis. And so I'd like to get your opinion on why silica is important, the silica products out there. Just tell me about all things silica.
Yeah, and I think we covered this from a different angle when we did our episode on silica, but silica is an interesting element and kind of fits into its own little category. I guess you could say it's got a unique history. It's got an interesting historical context. If you look in the, late 1800s when people were first starting to realize that there were these elements that plants required for growth, there was a list that was made. And that list was basically like which elements are required and which ones are not required. In other words, if you remove one of these elements, does that prevent a plant from going through its entire life cycle from start to finish, basically? And silica, it was quickly realized that silica, if you knock it out, plants can still go through their full life cycle without any silica, although there are more artifacts of these archaic studies than anything else, because as more and more people are starting to realize silica is actually very important for plants, it brings a number of benefits. And even though it's traditionally not considered an essential element, there are a lot of crops that will take up massive concentrations of silica. Cannabis is not considered an accumulator of silica. It can still take up, a fair amount, but it's not going to be a major constituent of its overall dry mass.
Mm-hmm.
If you're looking at some plants like horsetail, for example, horsetail is a very old species of plant and it takes up a massive amount of silica. It could be about 10% silica by dry weight. So it does accumulate and is considered a massive accumulator of silicon.
Jeez. Is this why silica wasn't included on a lot of older cannabis nutrient lines? I remember Wolfman talking about how some lines didn't even include any sort of silica.
Yeah. And part of it is because it was considered non-essential for growth. But we kind of talked about this in the episode on silica. I would definitely recommend people, if you're interested in learning more about this, definitely go listen to that episode. It is a deep dive. One of the things that we covered specifically was that silica sits underneath carbon on the periodic table of elements. And this is really important because it indicates that you have some kind of relationship. They share similar properties. And the way that I always describe it to people is think about silicon like a really fat version of carbon. It's not quite capable of making the same bonds with other elements, but it can still interact with those elements in similar ways.
Mm-hmm.
And where this becomes useful for plants is when you're thinking about, the amount of energy that's going into a plant is being utilized ultimately to pull CO2 out of the air and then make these carbon containing substances that do things like make up the cell walls, for example.
Mm-hmm.
And so there's this active process where energy is being spent to make cell walls. What if plants have the ability to take up silica passively and without any energy expenditure? What if they can insert silicon into the cell wall? What this does is it represents energy savings for the plant. That plant no longer has to spend the energy on reinforcing its cell walls with carbon containing substances. It can in fact use silicon to basically shove it into the cell wall and achieve a similar result, if not an identical result. Obviously,
Wow.
The cell wall is a lot more complex. There are multiple layers to the cell wall, and boron actually gets factored in here just as well as calcium does. But the idea is you're giving your plants the ability to save energy by allowing silicon to replace carbon as a constituent of the cell wall. It's not 100% replacement, but even if you gain, let's say, up to 5% in cannabis, and I don't know what the exact number is, but I'm just, let's just say hypothetically that number is 5%. That extra 5% of carbon availability can actually get funneled down to making more terpenes, and it can make more cannabinoids. And now you have this better expression in the plants. This is why specifically when growers apply silicon, they notice that the concentration of aromatic substances increases in the plants because there's no longer this bottleneck on carbon availability. The plants actually have the ability to take that carbon and to do something with it that no other element can replace, like monoterpenes and sesquiterpenes. They're 90% carbon by weight, and you can't fit silicon inside of the correct configuration to then replace carbon in that chemical structure.
So when growers see a good result of, silica making their plants more dank, it's not because the silica contributes to the cannabinoid production or terpene production directly, but it's the fact that it saves the plant on carbon because the plant is utilizing the silica instead. Therefore, you have more carbon, aka raw resources, to make more terpenes. That's a mind-blowing distinguishing factor there.
Yeah, and it also helps that silicon has useful mechanical properties. It's strong. It's resistant to, it can help increase a plant's resistance to environmental stressors like powdery mildew, for example, or massive variations in temperature and humidity.
Mm-hmm.
Even to some extent, the exposure to sunlight, the intensity of the sun can actually be reduced when you have structures that are reinforced with silica. It's just like the top of a greenhouse. They're made out of glass. They're made out of silicon dioxide, basically, and it's that glass is exactly what's happening with the plants. You get these little complex cross-linked sugars like the pectic acid residues, for example, and all these different layers of the plant's cell walls that actually become cross-linked with silicon And that mechanical effect that silicon has to increase the strength of the cell walls is specifically what allows them to resist disease pressures with greater efficiency.
Jeez. It's literally making the structure more sound and more difficult to disrupt.
Exactly.
That's
Yeah.
fascinating, man. Just really quickly, I'd be remiss if I didn't ask you about rooted leaf silica skin. Talk to me about this product. It looks unlike any other silica product that I've used, and I love it.
Yeah. So silica skin is an interesting product. It's made with a mix of fermented horsetail and hibiscus flowers. And those hibiscus flowers have some organic acids that actually help guide the insertion of silicon and the utilization of silicon inside of the cell wall constituents and the structures.
Jeez.
And, effectively, not only are we supplying the silica to the plants in a soluble form, so technically it is a silicic acid monomer form that the plants, take up and then they're capable of utilizing right away. But it's more about the throughput. It's more about giving the plants some kind of a signal or some kind of a stimuli to be able to have them actually utilize the silica instead of just having the silica be there and be present. Yeah.
Wow, man. My plants love it when I use this stuff. It's also in your foliar regimen.
Yeah.
The silica skin is a product I recommend people try. It's a good one to add to if you already have a regimen, it's a good one to add.
Yeah, it works great as a foliar spray. It has some really, really good synergy with solar rain. They have two different mechanisms of action, interestingly enough, because our silica skin, even though it's a high pH, it still does deliver silicic acid monomers to plants. And then solar rain, for anybody that's stuck a pH probe in solar rain, it's very acidic and it tends to drop the pH of the foliar sprays down maybe at about mid fours. But this synergy that exists between the two of them, I think, is made possible by the use of the horsetail ferment and the hibiscus flower ferments that we're using to make that. It just complexes the silicon and protects the charge in a way that allows the plants to get stable forms of silicic acid monomers before they polymerize. And, if they polymerize in the soil, that's fine because it just forms natural complexes that are going to be found in nature anyways, which, I think a lot of people already kind of know this to be true, is that silica can interact with some elements in the soil, some of the micronutrients for sure. But it interacts with these elements in such a way that can either tie them up or it can kind of help break it down a little bit further. We can kind of get into that a little bit too.
Yeah. I mean, it's a common thing in like bottled nutrient growers saying, mix your silica in first, wait some time before you add anything else. They're worried about locking it out. And they also say that the cloud that you see, like if you mix these nutrients back to back really quickly, sometimes you see this like clouding effect that happens. And they say that that's like a direct visual representation of silica locking out other nutrients. But you tell me what you think.
Yeah, I think a lot of times, because silica is very, very difficult to actually stabilize in a proper solution. So in nature, silicic acid is soluble up to about 100 ppms before it just starts to spontaneously condense. It goes through this condensation reaction where you have these linear monomers. They're just like, think about them like individual pieces, individual Legos. What ends up happening is you get so many in solution that they start to interact with each other, and then you form polymers. So you've gone from monomers being, a single monosilicic acid into these more polymerized forms. And you can get these polymerized forms that still exist in a chain, but eventually what happens is that chain becomes so long and it starts to precipitate out of solution, becomes heavier and heavier, and the water can no longer hold it. And what ends up happening is that linear polymer will start to cyclize. One end will kind of wrap around the beginning in the front end of it. And you start to get these species that resemble more like beads, for example, or they have these very complex three-dimensional shapes to them. They tend to be a little bit more wrong, a little bit more beady. And certainly people have noticed this with feed water solutions when they add the silica incorrectly or they add too much CalMag or whatever it is. This interaction ultimately leads to the formation of like silicate flakes you may have noticed.
Flakes.
Like
I know those flakes you're talking about. Yes.
Yeah, and those are the more complex networks. And if you were to look at under a microscope at that, you'd see in some cases, you'd see the linear chains, and in other cases, you'd see the more polymerized beads or the circular shapes. And certainly, depending on the pH, you can kind of guide the formation into a gel-like colloid. Think about silicon like it can form a gel-like colloid. Basically, it can form a network or a matrix that is gelatinous at a lower pH and then at a higher pH.
It does, yeah. Sometimes your silicic acid product, it's like sticky and jelly and weird. And I've seen that before. That's interesting.
Yeah. And ultimately, the point is that silica is very difficult to stabilize in solution in a high concentration. If you want silicic acid monomers, you got to do some wacky chemistry. That's why a lot of these pure silicic acid products tend to have extremely low pHs. The pH is what stabilizes the silicic acid monomers and it prevents them from condensing with each other. But it's certainly true that if you were to apply these products into your garden, you would first have to raise the pH to an acceptable range for your plants. And anybody who's used these products before, you guys know that even small amounts, half a mil per gallon or 1 mil per gallon, they do have an effect on the pH of the entire solution.
Mm-hmm.
And that's because that acid, again, it's there to help protect the charge. But once you raise the pH, that charge is no longer protected. It's susceptible, becomes exposed to things like oxidation reactions, where you can start to have some of these properties, these unusual properties of silicon start to come out. And, a lot of people may have heard that silica crystals can actually grow. Have you heard that before?
Right. Yeah.
Yeah. So like out in nature, silica will continue to arrange itself in these weird three-dimensional structures. It takes a very, very long time. The reason I bring that up is because what I'm trying to point out is that the nature of silicon as an element is very dynamic. It's always doing something, even if it's like perfectly, at a low pH or at a high pH or at a neutral pH. Silica never really remains happy, I guess you could say. It's always trying to do something.
I love that.
The goal for plants is to take up these soluble forms, these soluble forms of silicon and do something with them fairly rapidly. That's why foliar sprays of silica are so good, because it lets the plants directly access that soluble form of silica, and then it doesn't have to travel through the xylem. It doesn't have to spend time being inside of the plant tissue. It can get introduced into the outer layers of the cell wall pretty much immediately. And it can
Wow.
start to reinforce the plants. And that's why you see such fast and rapid results. Partially, the plant doesn't really have the ability to stabilize silicon by itself. It's ultimately destined for polymerization and insertion into cell walls. And so plants understand this. They like to take advantage of this phenomena, and that's why they respond so well to foliar sprays. Not only cannabis, but certainly other crops like cucumbers and zucchini, even tomatoes. All of these plants respond very well to soluble silicon being introduced across the leaf surface, because that's where it ultimately needs to go to help reinforce the cell walls.
Okay, this is great, man. And we have more to cover, but just to recap, that is so awesome. First of all, not necessarily considered or always considered an essential element, but so important for cannabis, specifically on the carbon savings. I loved how you pointed that out. You got to be aware of the pH change and make sure that the pH is appropriate. Watch the lockout effects and don't hesitate to foliar spray. Applying the silica foliar, you're saying, is a really good way to get it in there. So I think those are all really good tips for us to think about silica moving forward in our cannabis gardens.
Yeah. And I would tell people, don't get caught up in the phrase silicic acid. That acid implies that it's only something that exists at a low pH, but in reality, silicic acid is the exact same thing as hydrated silicon dioxide. It quite literally just represents the very first soluble form of silicon. So you have, if you took 2 molecules of water, which is H2O, and you took 1 molecule of silicon dioxide, which is SiO2, just count up the number of hydrogens and oxygens and silicas there and compare that to the formula for what is truly considered monosilicic acid. And what you'll find is that they're exactly the same. They contain the same number of hydrogens, same number of silicons, and same number of oxygens. So again, silicic acid is just the very first form of silica that is soluble. And the solubility factor is what defines bioavailability for plants.
Mm-hmm.
Plants can't take something up that's not soluble in water. They don't have teeth. They can't chew through a rock. So what they do is they excrete organic acids from the roots. Those organic acids will induce chemical weathering of silicate rocks. And in that process of chemical weathering, it will release this soluble form of silicon, which is silicic acid. But silicic acid can also be available at a high pH. So if you look at potassium silicate products, for example, those are high pH forms of silica. And even though they're high pH, they still technically release silicic acid monomers because they're fully soluble. And they are, again, the smallest form of silicon that's actually available to the plants. And silicic acid basically has silicon that's in a tetrahedral configuration with 4 hydroxyl residues, which is OH minus. So this concept of it being an acid isn't quite accurate, I guess you could say.
Well, all I know is a lot of those silica products cost an arm and a leg. So just go ahead and buy yourself some silica skin. My plants have just been loving it.
Yeah, it's a pretty cost-effective product overall because we're not taking it through this, crazy acid-base chemistry. We're actually doing it ourselves with fermentation of certain plants that contain compounds that are organosilicates, like in horsetail, for example, takes up a lot of silicon and it accumulates it into its structures. And it's nice for us to be able to reutilize that to help guide silica metabolism in other crops. And then, like I mentioned earlier, hibiscus flowers contain organic acids that we've seen work really, really well with.
Can I ask you something? And please take this in the spirit it's intended.
hmm
Is rooted leaf just like the world's most advanced and dialed in KNF? Like, it sounds like this is a fucking amazing ferment that you have. Like, I love that your products are so formulated, but it's at the end of the day, they're mostly just natural fermentation processes, right? That's so cool.
Yeah, it's entirely modeled off of fermentation chemistry. There's a lot of different layers to it, but ultimately, yeah, what we're trying to do, the purpose of these formulations is to kind of represent what happens in nature. And in nature, plants use certain types of organic acids to help complex with silicon, just a function of how plants have evolved. And certainly when we look at the plants that do it best, we start to get a little bit of inspiration. And that inspiration is in a molecular format, I guess you could say.
It is so cool, man.
Yeah, it's definitely, there are aspects of advanced chemistry because obviously, we're trying to make things concentrated, cost effective. We need the ability to make things very consistently from batch to batch. And so there's this aspect of advanced manufacturing, but what it's ultimately rooted in is fermentation chemistry and the way that things happen in nature.
It's so cool. You even put the plants that are used on the outside of each bottle. If you look at the side of each bottle, you can see the plants. It's really cool that you did that.
Yeah, and a lot of other brands will have the plants listed as non-food ingredients, but we did, and this took us a long time. I know we're getting just a little bit off topic here, but it took us a very long time to actually prove to the regulators that we, through the fermented plant mixture that we're actually deriving these macro and micronutrients. That's why you'll see when you look at our products, you'll see in the derived from statement as opposed to the non-plant food ingredient statement. We were able to demonstrate that the plant extracts, like for resin bloom, for example, the jasmine and the ginkgo, those are contributing to the overall concentration of potassium, but also the specific forms of potassium that we guarantee that product is derived from. And I don't think there's any other brand that's achieving this right now. I don't think that anybody's done the same level of work that we've done.
That's cool. And they want you to prove that always. So that's cool that you took that extra time and did that extra work. Rooted leaf nutrients, you've been hearing about them on this episode, and code GROWCAST gets you a whopping 20% off at rootedleaf.com. If you're not completely satisfied with your nutrient regimen, you have to try Rooted Leaf. If you're sick of pHing whatever you're using, you got to try Rooted Leaf. Start with filtered water, add their plant-derived fertilizers at the recommended dosage, no need to pH, just mix and let it rip. I have never been so impressed with my growth rates, with my trichome production, and like I said, the best part, no pHing. I've used it on my outdoor garden. I've used it on my worms. They're still fat and happy. I've tested the pHing myself, or the lack of pHing, and let me tell you, it works fantastic. Couple this with the Rooted Leaf foliar program, and your plants are going to be absolutely ripping. They are microbe friendly, they're worm friendly, and best of all, you don't need to pH these amazing nutrients. Just hit those roots with the liquid dank sauce and watch that wizard juice turn your plants into the stinkiest harvest yet. You can find it at rootedleaf.com. Code GROWCAST saves you a massive 20%. Use it on your cannabis, use it on your fruits and veggies. You will not go back. No pHing required. And clearly a lot of thought has gone into the formulation of this line. So I implore you to try at rootedleaf.com and always use code GROWCAST. It helps them, it helps us, and we really appreciate you listeners for supporting the amazing Rooted Leaf. Okay, so you talk about these micronutrients that are needed in small amounts. Manganese is another one that I see. Sometimes it diagnoses a deficiency diagnosed in my Discord. It's one of the ones that I see on my radar a lot. Tell me about manganese and why it's important.
Manganese is a really interesting one. It's most famous for playing the role in the what's called the oxygen evolution complex. And it's basically where plants use the power of the sun to split molecules of water apart. And this is fundamental for the generation of the proton gradient that ultimately leads to ATP biosynthesis. So it is a crucial step in the process. And what happens is the oxygen evolution complex itself contains manganese It's a cofactor that contains manganese, and the manganese actually allows for the transfer of electrons to occur. And so this is really important in grows where you have high light intensity and your plants are becoming thirstier and thirstier. Again, when your plants are taking up water, ultimately the purpose of that water is to get split apart so that you can get this proton gradient that starts to form and leads to the biosynthesis of ATP, which is energy for your plants. So if you start to notice in your garden that if you crank up the light intensity, the plants have an increased appetite for water and they metabolize that water more efficiently, it's really manganese that's at the core of that reaction of the splitting of water molecules apart. And so I always find that there's a little bit of additional need for manganese during periods of high light intensity. So for example, as you're acclimating the plants, if you start them off under weak lights or soft lights during their early vegetative stages, it's really in that transition to a higher light intensity with more water being applied to the plants that a little bit of additional manganese can go a long way.
Mm-hmm.
And there's something to be said too about using particular light frequencies, particular spectrums of light, like the slightly more orange and red that comes off a high pressure sodium bulb. That will kind of stimulate the oxygen evolution complex because that light energy in that spectrum is actually being funneled down the oxygen evolution complex anyways. So,
ooh, that's interesting. Now the splitting of water, you've highlighted the importance of this before on the episode with about potassium, right? So you talk about this being important because hydrogen is so important as a building block. And like you said, starting that chain reaction. But am I mistaken? Is it manganese and potassium that are both so crucial to get that plant to drink as much as possible, which is something we want?
yeah, potassium is really important, but the way that it behaves is a little bit different than manganese. Potassium is monovalent, and so it's got fundamentally different charge characteristics than manganese does. Manganese actually facilitates the transfer of electrons and it allows for this water molecule to be split apart. Effectively, what ends up happening is manganese is the thing that allows plants to oxidize oxygen, which is a very, very difficult thing to do. They take electrons away from it, basically. The presence of potassium and the flow of potassium is a little bit different. But yeah, the concept there overall is actually quite true. And I'm glad you brought that up because as you get these additional concentrations of potassium, you're inherently going to have better water metabolism and better flow into the plants. Everything from the stomata opening and closing to the activation of some of these enzymes being turned on and off. Potassium may very well actually interact directly with the oxygen evolution complex to either turn it on or off. And part of that mechanism there is just the sheer abundance and the presence of so much potassium that it can kind of guide the flow of water effectively. But at the actual active site, manganese sits and it becomes tethered or complexed with the rest of the protein structure, and it allows for this flow of electrons to be passed back and forth in a way that splits the molecules of water apart. And then from there, that's where you start to have these more downstream effects occur, like the generation of the proton gradient. And then from there, the biosynthesis of ATP molecules.
So manganese a little more minute and a little bit more fine tuning, potassium controlling a lot and mechanical stuff, like you said, opening and closing and things like that.
Yeah.
Very cool.
Yeah. And a lot of these, I know we talked a little bit about these micronutrients just being present at the active sites of enzymes where they're actually doing the work. They're facilitating the building up or the breaking down of various substrates and leading to the formation of things like chlorophyll and so on and so forth. But, the same properties that these micronutrients have in terms of their ability to hold and release charges is also what makes them so useful in the context of antioxidants inside of plants. When we look at some of the most important antioxidants inside of plants, like superoxide dismutase, for example, and catalase, you knock these things out. And, there's other peroxidases as well. And certainly some of these may contain just sulfur inside of them as their active site. But the ability for them to convert so rapidly between their reduced and oxidized forms allows them to form the basis of redox networks inside of plants. So now we're not only looking at micronutrients in terms of their ability to get work done, but also in terms of their ability to soak up excess oxidative stress. And this soaking up of excess oxidative stress is what contributes to their sort of antioxidant potential. They can hold that charge, and that charge can be further handled by the more complex protein or the enzyme that's associated with binding that particular element, I guess you could say. So like superoxide dismutase, for example, has a very specific role that it plays. and it can catalyze what's called a dismutation of superoxide and convert it basically into oxygen and then hydrogen peroxide. And the oxygen itself isn't going to be harmful for the plants. The hydrogen peroxide can get further broken down by other antioxidant mechanisms. So,
Jeez.
yeah, the conversion of that happens ultimately because of the presence of some of these micronutrients like manganese, for example, copper, zinc, iron. There are these various forms, I guess you could say, of these enzymes like superoxide dismutase. There's a couple of different flavors of it depending on where exactly we're looking. If we're looking in the mitochondria versus the chloroplasts versus the cytosol, these are all different compartments within the plant cells. And the forms of superoxide dismutase may actually change a little bit in terms of what's in the active site, just based on the dynamics of that particular organelle that we're talking about. And, one of the things I'll kind of drop as a hint here for people, and we'll kind of get into this in the next episode that we do on the Calvin cycle. But a lot of times when we're talking about things like ATP and ATP biosynthesis, it depends on where the ATP is made. If it's made in the chloroplast, the mechanism of that formation is fundamentally different than the mechanism of formation in the mitochondria. And it has a lot to do with the actual direction that the complex may face. So like in the mitochondria, for example, ATP synthase actually faces back down into the mitochondria, and the pH of that tends to be pretty neutral. Maybe it might drop down about 6.5 or 7.0, but it's not that acidic. In the chloroplasts, on the flip side, the ATP generating functional group is actually facing outward, meaning the ATP is pumped outside of that. And inside of the chloroplast, the pH can actually be pretty acidic. It can drop down very, very low. Part of this is the proton gradient that's generated from the splitting of water. But I also just want to kind of bring that up and give a teaser to people, because the effect is ultimately the same, right? ATP synthase will make ATP, but the chemical environment in which the ATP is made is fundamentally different. And because you have these differences in chemical environments, that's why you've got these different forms of superoxide dismutase. Yes, it's one enzyme, but it may bind to manganese, or it may bind to copper, or to zinc, or to iron, kind of depending on where exactly we're talking about in the plants.
So it depends on where in the cell it's produced, this ATP. Thinking back to the phosphorus episode, this kind of time bomb of conserved energy, as you've kind of put it, having different properties depending on where it's produced in the cell.
Correct. Yeah. And that's a little bit nuanced point, because ultimately it doesn't matter, because the ATP is going to be generated one way or the other. But I think it's also important to understand that there are differences in the chemical environments which ultimately impact what the form of these other enzymes is and how the micronutrients may actually get utilized.
It's wild.
Yeah. So, the point at large ultimately is that the micronutrients we kind of went through in today's episode, we looked at them in the context of active sites of enzymes that do things like make chlorophyll or make cell walls. But it's also important to understand that they're very useful as antioxidants. And a lot of the most important antioxidant enzymes and defense systems at large in plants actually rely on and utilize the electrochemical properties of these micronutrients in a way that allows the plants to resist oxidative stress and deal with oxidative stress very efficiently.
Love it. Let's move on to the next micronutrient. This one comes up quite a bit, molybdenum. How should we be approaching molybdenum? Where does this mineral even come from?
Yeah, that's a good question. And I think, for the larger context in terms of how micronutrients function in plants, I think it's important to understand that micronutrients are not really accumulated. Like calcium is actually a good one for us to talk about in contrast, because when your plants take up calcium, the goal of that calcium is to get sunk into a cell wall. Plants take it up in its soluble form, and then they deposit it into the cell wall, where it typically is not repurposed. It's not broken down again. There is some movement of calcium between cells. We kind of talked about this during our episode on calcium waves in plants. And there isn't enough forward movement of calcium ions during periods of calcium waves to actually fulfill the nutritional needs. But there are some ions that will travel across the plasmodesmata that make up the cell walls and connect the individual cells to each other. So there's a little bit of transfer, but not enough. Micronutrients are not taken up and deposited and sunk into cell walls nearly to the same extent that calcium is. Instead, they're actually used at the active sites of enzymes. So when we're looking at doing things like holding a charge, copper is a good example of something we can talk about, because everybody knows copper can hold a charge very well. It can conduct an electrical charge. That's why copper is ubiquitous in electronics. inside of the actual hardware, because the properties of copper are such that it can hold that charge and pass it around.
Mm-hmm.
Well, enzymes in plants also do the exact same thing. They sometimes, in order to facilitate a chemical reaction or a biosynthetic reaction, they need to be able to hold a charge and then use that charge to achieve a certain type of work that's being done. That's where we're going to find a lot of these micronutrients, and the roles that they play is in the actual active site of enzymes. That's where the energy goes to. And then that's the actual thing that powers a conversion reaction. If you're taking a building block and further transforming it into its final metabolite, or even into just a different step, and then feeding it into a different series of enzymes, which is oftentimes the case in plants. This is where the role and function of micronutrients is most relevant. So with molybdenum in particular, molybdenum is oftentimes associated with nitrogen reduction, or nitrate reduction, I should say. So that takes a lot of energy going into the equation, and molybdenum being at the active site of the enzyme nitrate reductase is what allows plants to actually convert it efficiently. So I think a lot of times growers who are feeding high concentrations of nitrates to their plants have heard from agronomists, or maybe seen for themselves, that adding just a little bit of extra molybdenum can actually go a very long way. And I'm not talking about, adding a huge quantity. I mean, even if you increase, let's say the sweet spot for your plants in your garden, based on how you're growing, let's just say hypothetically, it's 200 parts per million of nitrogen, and your molybdenum concentration, your optimum is about 10 ppms. Even if you add an extra 1 ppm to that 10 ppm, that's a 10% increase.
Right.
And that's the important thing for people to understand, that adding just a little bit of extra micronutrients, when you understand the dynamics of how the system plays out at large, can be very beneficial. But adding too much can be counterproductive, and you won't see the types of results. Or even worse, you're just going to waste the micronutrients, or they're going to accumulate in the plants, and you're not going to get a good, clean product at the end of the grow.
And I've heard about this link between molybdenum and nitrogen, right? That the plant can't utilize nitrogen properly if there's not enough molybdenum present.
Yeah. And like I mentioned earlier, part of the function here, which is actually kind of a ubiquitous function, if you guys hear me say this a couple of times, it's because it's true of these micronutrients in general. And when we're looking at something specific like nitrate reductase, it's the molybdenum that allows for the transfer of electrons to occur. So you get this gradual reduction of nitrate first into nitrite. And, it's a multi-step process, and it takes a lot of energy. So this is just one link in a larger protein complex, or a chain of reactions that happens. But the specific mechanism, again, is there's this transfer of electrons into nitrate, which is fully oxidized, and this conversion process begins to take place. This electrochemical functionality is ultimately what defines the micronutrients, about 90% of their function, I'd say. There's other elements that are like boron, we'll probably get into here in a couple of minutes, but boron is actually a constituent of the cell walls, and we'll kind of get into that a little bit more. But yeah, the important thing for people to kind of understand is, for these biochemical reactions to actually take place, when you're talking about transferring electrons, or you're talking about the flow of energy through the plant, these cofactors, these micronutrients that sit at the active sites of these enzymes, are where the spark actually happens, if you will.
And you need just a little bit of those micronutrients, usually to do just like you said, one or two things, as opposed to some of the other ones that we've covered in the past. This is painting a really clear overall picture to a layperson like myself, who didn't take high school chemistry, because I stopped going to school before they got to teach me chemistry. So this is all new to me. No, you mentioned boron. We got to go there, man. Boron comes up all the time. When it comes up in the cannabis world, Nick, is with hollow stems. People talk about hollow stems, and they say that you need to up your boron. I don't mean to cue it up, with that specific. Tell me what you think of boron in general, and then tell me what you think of the hollow stems theory.
Yeah, so boron is interesting, and I do think there's a little bit of a misunderstanding about boron and the roles that it plays specifically. Again, it's one of these elements that's essential for plant growth, meaning if you knock boron out, you start to get major issues with cell walls. But I think the thing that people misunderstand about boron is actually not in the context of the roles that it plays, but rather in this kind of theory about what's called biochemical sequencing. And I see a lot of people talk about this quite often, actually. And I think the whole concept, we may actually have to do a separate episode about this altogether, because this myth of biochemical sequencing is actually just bro science at best, and it's kind of misleading at worst. So oftentimes boron is attributed to being the very first element that's in this biochemical sequence, meaning that plants first have to access boron. And then there's this elaborate description about how, like, calcium is a truck, it carries nitrogen on its back or some weird stuff like that. None of that is true at all. Okay. I just want to get that out there first and foremost. That's not at all how it works. What happens is boron forms diester links. It's basically, think about like a boron complex, basically. Boron complex is these sugars that are present inside of the cell walls, and it creates structural stability in the actual cell wall. It does help reinforce. It becomes deposited just like calcium, and it participates in the formation of the actual structure itself. But again, boron is not present in a very high concentration in plants. You may be able to take up 150 to 200 parts per million of calcium, and the bulk of the cell wall is going to be reinforced by calcium. And you may also have silicon coming along. And of course, carbon in the form of pectic acid residues and all the different layers, hydroxyproline-rich glycoproteins. There's all kinds of different sugars that are present. There's probably at least a dozen or 2 dozen different flavors of these sugars that are carbon containing, that are calcium binding, that are silicon binding as well. And of course, boron fits into that, but it's such a small percentage that I don't think your plants are ultimately the make or break thing isn't going to be whether or not, you have these very high concentrations of boron being present there. So oftentimes with hollow stems, it's more a function of a carbon deficiency, because if you don't have pith in there, it's directly connected to and associated with a carbon deficiency in plants. Ooh. If you have ample concentrations of carbon, you can actually get pith. And there is something called pith autolysis. Auto meaning spontaneous, lysis meaning to break apart, like hydrolysis, water splitting, hydro meaning water, and lysis meaning to split. Pyrolysis is another one. Pyrolysis, pyro, obviously fire. Lysis is to split. So anytime that you're burning, wood in the backyard and you're having a bonfire, you're pyrolyzing the material. You're using the power of fire to split molecules apart. So there is something called pith autolysis. And pith autolysis occurs when plants don't have access to enough carbon. They start to cannibalize the carbon reserves. And the first place that they go is the pith. The pith itself is an actual structure. It's a layer of the plants that allows for higher concentration of minerals to be present and stored and captured. It allows for water to actually be stored in this sponge-like
center layer. Right?
Yeah. And, it also provides some mechanical resistance against disease pressures. So if you have something that's like a pathogen that's present inside of the soils, it can get solubilized and taken up through the transpiration stream. And that's oftentimes how plants can get infected with diseases. Think about that pith like a filter. The water is being forced up through this membrane, effectively, that's a filter, and it can catch and prevent diseases from occurring within the plants, or it can at least localize them and prevent the spreading of it. When your plants have hollow stems, it's typically a sign that their growth is imbalanced. They don't have enough access to carbon, or maybe they have too much nitrate, which draws reduction power away from carbon metabolism, and they start to break down and cannibalize that layer of pith, which leads ultimately to things like hollow stems and hollow stalks.
Wow.
That's generally speaking, that's true in most cases. Now, it could be a strain specific thing too, where you have a stem that may have a little portion of it at the very dead center, could be a little bit hollow, but that could be reinforced by that white layer of pith leading out to the outer edges of, the stem or the stalk, which could ultimately be green and enriched with chlorophyll. So I've never really heard about boron being like the chief contributor to this stuff. I think that anything that happens with the cell walls is ultimately going to impact boron metabolism, ultimately, because that's where boron goes. It becomes a constituent of the cell walls. But again, it's not such a high concentration that you're likely to see these things before you experience issues with calcium or with carbon or even with silicon. Boron is kind of like down the pipeline a little bit. It's not like the primary thing. And chances are, if you have a boron deficiency, that ultimately, in effect, can lead to an imbalance of carbon metabolism leading to cell wall formation. So the actual problem itself could be caused maybe not by boron, but maybe by a lack of structure that boron actually fits into and sits inside of, which is the cell wall constituents.
I want to do an episode that's like 3 analogies to rethink the way you think about cannabis nutrition. Because it sounds like, we could talk about calcium as kind of the bones of the structure, like the 2x4s and the drywall and things like that, right? And then you talk about interweaving this silica and how the silica is kind of like, earthquake proofing and maybe insulation, right? It kind of weaves in there, makes things stronger and helps with heat and cold and things like that. And then what does that make boron in this construction scenario?
I would say boron is like a tiny little bridge that connects otherwise separate constituents and structures. I mentioned earlier that basically they're diester linkages. They're borate containing compounds that link some of these constituents together. So I would say think about it like it ultimately just connects things together and reinforces
the joint
the
plates.
structure overall. Yeah, it's like when you're driving down the freeway and if you're driving down a windy hill, you have the guardrails on the side. Well, the guardrail itself, if you just take a single piece of that guardrail and disconnect it from everything else, the overall strength of that becomes significantly weaker, because if you don't have your guardrails that are linked together over a long distance, you don't have the ability to disperse a huge force coming into that guardrail very effectively. In other words, if you crash your car into a guardrail, it's really the whole length of the guardrail that takes the energy, and it's through the linkages that allows that dispersion of force to occur, and thereby ultimately, hopefully saving whoever is unfortunate enough to crash into it. But again, if you just have one of these that's disconnected from the rest, your car will probably plow right through that, and there's going to be very little, if any, resistance that's effectively afforded. So that's kind of what boron does, is it creates these structural relationships between the otherwise separate regions of the cell wall. Yeah, I hope that helps.
I need these analogies. These are exactly what I need. That's the type of shit I remember. So speaking of guardrails, let's talk about iron. Hopefully it's like, steel or something a little better than wrought iron. But this is another micronutrient that we have to cover. And again, this is one that I see supplemented a lot. There's a lot of products. There's an iron and zinc product that I have on hand. You know what I mean? Mm-hmm. Why is iron important to plants? How do we identify those deficiencies? And how do we treat it with rooted leaf, preferably?
Yeah, so iron, kind of the same thing as, these other micronutrients, the ability that it has to hold and release a charge, and it can really power certain types of processes. I think one of the most famous examples is for chlorophyll biosynthesis. And a lot of times when people look at their plants and they see them yellowing, could be a variety of things. Could be nitrogen, that's usually the culprit. Could be magnesium, obviously as a constituent of chlorophyll. And then it could also be related to iron. So a lot of times when people have iron deficiencies, their plants will exhibit a yellow coloring. You start to get a little bit of chlorosis happening, and your chlorophyll biosynthesis rates go down. And it's specifically because iron plays a role in the enzyme that synthesizes chlorophyll. There's a couple of different steps in the operation, but the point at large is that when you're dealing with this green pigment that powers all of the plant's activities, iron is not so much an essential constituent of that, because it's magnesium that sits at the active site, but rather iron catalyzes the reactions that are necessary to do things like form the actual structures for chlorophyll. It's a multi-step process. I think there's 7 or 8 steps involved in chlorophyll biosynthesis. And at least for a couple of those steps, iron is required as a cofactor to actually allow that to happen.
So another one of those pieces of the puzzle that needs to be there. Is that why it's used in chelator things? Is that one of the reasons it's used, because of the charge and the fact that it's like a catalyst?
Yeah. So are you talking about chelated forms of iron?
Yeah, like iron EDTA and the stuff that is kind of not so good for the environment, or at least sticks around for a long time. It's what I see a lot as a chelator on the back of salty nutrients.
Yeah. So iron EDTA and DTPA and EDDHA, these are all synthetic chelates. They're not really bioavailable forms of iron. And I think
I didn't know that.
The issue of bioavailability. Yeah. And I think the issue of bioavailability factors into micronutrients, because these transition metals in particular, they're susceptible to oxidation. So when you have, and this is purely from the standpoint of the chemistry of the elements, when you have a solution that has a pH above 7.0, you're very likely to create the hydroxide forms of these, because, there's hydroxyl groups that are more present in high pH. So as the concentration of these hydroxyl functional groups, these OH minuses that are kind of floating around in the solution, they tend to attack these micronutrients and render them unavailable for plants. That's why a lot of the chelated forms of iron happen to be acid forms of iron.
To keep that pH low. Okay.
Yeah, to prevent that element from becoming unavailable to plants and forming its insoluble and unavailable hydroxide form. This is ultimately what happens when rust is formed. It's basically the oxidation of iron, and it changes oxidation states. And in order for plants to access it, it needs to be in reduced form rather than an oxidized form. So when we make our micronutrient package inside of Primer B, for example, we have a bunch of organic acid chelates of these micronutrients. And what we're finding is that the chelated forms themselves actually extend above a pH of 7 in terms of their availability. In other words, the charge on that iron is protected sufficiently so that as the plants will go through their pH ranges naturally, they're never going to have a pH range where that iron or these other micronutrients falls out of solution. And this is why we can basically guarantee a true solution that contains 100% bioavailable forms of nutrients for plants across a very, very wide and broad pH range. In most normal circumstances, the pH would be a limiting factor for the availability of these elements. But when you start factoring in chelating agents, one of the purposes or goals of using a chelating agent is to extend and broaden the availability of that element so that it can be available at a little bit lower pH and it can remain available at a little bit higher pH overall. Mm-hmm. Again, it's the interaction that these chelating agents have with the actual charge on these elements that is capable of protecting them and making them less susceptible to doing things like falling out and becoming insoluble or converting from the soluble form of iron to the insoluble form of iron and the unavailable form of iron for plants.
No, that's why it's so important from a home grower's perspective to not just necessarily add more of the mineral if you're seeing signs of deficiency, right? Micronutrients are a perfect example of that. Most of them taken up at a lower pH. If you look at the pH uptake chart, what you'll notice is a lot of the macronutrients are taken up at a slightly higher, right? So it's like you have to identify why this nutrient isn't being absorbed, whether it's not present or it's not being fully utilized. Those are two totally different solutions.
Right. And I think, to that point too, if you see a micronutrient deficiency and you're in the vegetative state, a really good solution would be to try a foliar spray of some micronutrient containing products, because the micronutrients being at the active site of enzymes, the leaf surface is a very, very active place. That's where a majority of the nitrate reductase enzyme exists. And so if you're trying to supplement some elements that are used for things like chlorophyll biosynthesis or for nitrate reduction or even for the splitting of water, that happens near the leaf surface. It doesn't really happen as much down in the roots because the roots don't have access to the same level of energy that the leaves ultimately do. I mean, the leaves are the ones that are accepting energy from the sun and then powering all of these other biochemical processes. Wow. And it's at the spot where a lot of the micronutrients actually get utilized. Not all of them, obviously, but certainly there's a high level of activity, enzymatic activity, which utilizes micronutrients. I will say the other thing about iron too is that iron oftentimes is present inside of what are called iron sulfur clusters inside of plants, and these also help facilitate the electron transfer. So when we're looking at things like the photosystems, for example, the way that the electrons flow and the way that the reduction reactions happen is dependent on these iron sulfur proteins like ferredoxin, for example. It accepts electrons and then it funnels those electrons down to ultimately produce both ATP and NADPH, which are kind of like the byproducts, I guess you could say, of photosynthesis. That's the actual energy currency that plants depend on to power literally every other reaction that happens within plants. And so there's this direct fork, if you will, where the energy coming in from the sun gets diverted down to a variety of these pathways. The most common pathway is the Calvin cycle, which we'll kind of get into in a separate episode probably. But plants, the majority of their energy is focused on taking carbon out of the air. That's kind of what plants do. They use the power of the sun to ultimately suck CO2 out of the air. But there's a fork in the road where maybe that energy from the sun can go towards the reduction of nitrates, like we talked about just a few minutes ago. That represents one flow of electrical energy. And then another flow of electrical energy could be for chlorophyll biosynthesis. It can be used for ATP and NADPH biosynthesis through ferredoxin. So yeah, the iron sulfur complexes are pretty important overall. And those are again found
in that photosynthetic chain.
Yep. And they can also be used to generate energy in the mitochondria besides, their roles that they play in the chloroplast, which is where all this, energy from the light is ultimately being funneled through first and foremost.
Are they being used up? Is this why I sometimes see okay, so first of all, what I have been kind of taught is a sign of A micronutrient deficiency, specifically something like iron or zinc, is when you're getting that yellowing, like you had described, that yellowing. But a lot of the times, anyways, what I've been told is that it's like that yellowing on the edges of the new growth. Like someone took a highlighter and highlighted the margins of your newest nodes' edges. Do you agree with that being an iron deficiency?
Yeah, it's tough to say for sure because the elements themselves and how they ultimately factor into what constitutes a deficiency or not. There's a lot of different things that could be happening.
It's complex, sure.
It's very complex, but yes.
Is that a possibility? Yeah. So a lot of times when I see that, I feel like it's during times when the light intensity has been increased suddenly. I don't know if that is a hypothesis you could get behind or not.
It is, yeah. And I think part of it is as you increase the light intensity, it can create a positive stressor for the plants to, let's say you're giving them 200 ppms of nitrogen. If your light intensity is only 50% of what it can be, there's kind of like wasted potential, so to speak. And as you crank up that light intensity, more and more of that nitrogen becomes effectively utilized. Your plants will experience a higher rate of chlorophyll biosynthesis, for example. So they're capable of making more green pigments because they have access to more light energy and they have access to more nitrogen. So this is ultimately what happens is your chlorophyll density kind of increases in proportion to that. And, similarly, if we're talking about these active sites of enzymes that produce these pigments and are responsible for these biochemical reactions, it makes sense why you have an increased need for these micronutrients or why you start to see some yellowing or some chlorosis or even some senescence occur when the concentration of the micronutrients doesn't match everything else. You could have enough light intensity, you could have great airflow, you can have all the concentration of the macronutrients that you need. But if your micronutrients are the bottleneck, it will become the rate limiting factor for chlorophyll biosynthesis. And that's where you start to see some of this interveinal chlorosis start to manifest itself. It's because you don't have enough micronutrients to actually power the reactions at the rate at which they need to be powered. You can have one enzyme making one step in the process of chlorophyll, or if you've got multiples of that enzyme, you obviously need multiple active sites, which means you need more and more of these micronutrients that are kind of available for the plants to take up and utilize.
That makes a lot of sense. If that's the bottleneck, that's why you're getting that drop in that chlorosis. Everything else is being kept up, but this one small micronutrient.
Yeah. And it comes down to density overall. If you took 1 square centimeter of a healthy plant's leaf surface and you looked at it under a microscope, what you would find is that there's a particular density. There's so many chlorophylls per, whatever unit of measurement you want to look at. And then same thing with rubisco. So if you can increase the concentrations of rubisco, you can have a leaf that's still the same size overall, or you're looking at the same area, surface area overall. You just have higher concentration of these, which means that plant's going to be more productive because it has more chlorophyll. It can capture more energy from the sun. And if it's got more rubisco, it can create more soluble species of carbon, create more sugars for the plants to then accelerate their growth. And so again, you could have one plant versus another plant that look the same overall. Ultimately, they have roughly the same surface area to their leaves, but it's the density of chlorophyll and rubisco that will ultimately determine how fast the plant is capable of growing. You may notice that one just grows significantly faster than the other, and it could have everything to do with the concentration of chlorophyll and the density, I guess you could say, of both chlorophyll and rubisco. And that's where the micronutrients can really go a long way. A little bit of extra micronutrients, particularly in very intense grow environments where you have high light intensity, high concentrations of water that are always enriched with soluble forms of nutrition for the plants. That's really where you're going to find benefits with a little bit of extra micronutrients if you've got everything else kind of dialed in.
I love it. One more final stupid question. Why are micronutrient inputs usually like tinted red?
That's a good question. It could just be some artificial dye.
Right? It's the red one. It's always the red one. Like you know what I mean? The micro is always the red one. Why? Why is that?
I think it could just be the, artificial colors and artificial dyes that are
fun
inside of some of these products. I think in some cases, a lot of the optical properties of these minerals, I think copper sulfate, for example, is just naturally blue. And so you may have optical properties of the compounds themselves. But yeah, as far as the actual products that are out there on the marketplace, it could just be the artificial dye and the artificial color. Primer B is this very bright crimson color. It's very red, but that is a function of the pigments that we use to make that product. It's actually the exact same pigment that gives primer A its vivid blue color, except those exist at two different pHs. Primer B is a lot more acidic, and part of the
Whoa.
acidity obviously is, the organic acid complex that keeps those micronutrients stable and bioavailable for plants. But yeah, that's the fun fact of the day for you. Primer A and
That
B
is sick.
contain the exact same pigment. It's just a different pH that gives one a kind of a bluish color, and then primer B is just like bright crimson. It's almost pink.
It's like that tea that turns blue when you add lemon to it. That's wild, man.
Yep.
Listen, this was a great deep dive. I am going to change a few things in my garden. The application of micronutrients through a foliar spray. That is something that I'm definitely lacking on, and I'm going to institute more of. Staying on that pH and understanding the different ratios of these micronutrients. These are all big breakthroughs for me on this episode, and there's been many, many more. I'm sure the listeners love this. So thank you, Nick. Where can people find you before we wrap it up?
Check us out on Instagram, The Rooted Leaf, and definitely check out our website, rootedleaf.com.
Rootedleaf.com. Go and grab it. Go grab some silica skin. Go grab some CalMag fuel, or do yourself a favor, grab a starter kit. Use code GROWCAST, 20% off at rootedleaf.com. Thank you, Nick. We appreciate you, man.
Absolutely great to be on.
Thank you, brother. We'll have you back on again soon. Like we said, everybody, we'll do the Calvin cycle. We'll get some of these non-soil fertilizer elements. Some more deep dives coming your way. So don't touch that dial. Thank you for tuning in. This is Nick from Rooted Leaf and Jordan River signing off, saying have a great day. Be safe, everybody, and grow smarter. That's our show. Thank you so much for tuning in. I appreciate each and every one of you listeners. I have refocused on membership and on the show now that my schedule has opened up. I'm going to be going to the islands for a while. Give me some really great downtime to work on new membership benefits mostly, and also some new content for the public-facing show. So don't touch that dial. And of course, come check us out at growcastpodcast.com/membership, where we're about to drop a whole new content flow with more member videos, with more giveaways, membership exclusives like genetics and products that no one else can get their hands on. It's going to be a brand new Growcast membership. So jump in today, why don't you? And stay tuned for the big new membership drop, as well as some goodies on this show. Go to growcastpodcast.com to see all the things, the membership, the seeds. Next year's classes are going to go up there soon, and I look forward to seeing you in person. Most of all, though, I just appreciate you tuning into this show and trusting us with your garden. We will continue to work tirelessly to educate you, to serve you, and to get as many people growing as we can. So let's overgrow this thing, everybody. Hope you give seeds to someone in need, and I hope you stay safe out there. We'll see you next time. Bye-bye.
Silica never really remains happy, I guess you could say. It's always trying to do something.